5C.2 Triangle Congruence Proofs. Okay, this is an extension of the last lesson, so we're just going to be using what we learned in the last lesson and applying it to proofs. But here's a little warm-up at the beginning. The first, this says, are the following pairs of triangles definitely congruent? Well, looking at this first diagram, I've got one set of sides that's congruent, and here's a second pair of sides. That's not enough, though, with just two sides. Need something else, but I've got the shared side in the middle. So I can say that this is congruent to itself. And then after that, I can say, yes, the triangles are congruent by side, 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 triangle congruency theorem. So I use the reflexive property to get the segment in the middle and then SSS. Okay. On this next one, I've got this one pair of sides there. Here's a second pair of sides, but again, that's not enough. This time, though, I can say that these vertical angles are congruent. That's the vertical angles theorem that allows me to say that. And then I can say the two triangles are congruent. I got two sides and an angle. I just need to decide now if that angle is included or not. And if you look at the top triangle, if I look at those two sides, the ones that are marked with the congruent symbols, the angle that they form is right there. So this is the included angle because that's where those two sides meet. And the same thing on the bottom here. Those two sides meet at that angle. So it's an included angle, which means I need the A to be between the two S's. So that's the side angle side congruence theorem, triangle congruence theorem. Okay, on the next one, I've got these, it's pretty small here, but I've got these parallel sides, and that's going to be the key to this problem. So I could use the reflexive property again because I have that shared side in the middle, but this is asking what pair of angles are congruent. So I'm going to think of the two parallel sides as lines like that. So I call those tracks. And then when the tracks are parallel like they are here, then if I use a transversal, that's a line that crosses over both lines, then we can use different types of angle pairs that are congruent. So I've got three different transversals to choose from, but I want to choose this one that goes down the middle here, because that one, along with the other two purple lines there, creates angles that are in both triangles. So if I use this angle and this angle, they're on different sides of the transversal. They're on the inside of the tracks. So inside of the tracks, interior, different sides of the transversal, alternate. So these are alternate interior angles. So I can say that this angle down here, which I'll call angle ABD, is going to be congruent to this angle up here, which I'll call angle BDC. And that's by the alternate interior angles theorem. Okay. All right. So now let's get to some actual two-column proofs. Okay. So our first reason is pretty much always going to be given. That's the given info, which you can see is exactly matches up with the given info at the top there. Okay. So the first thing I do is after I write given for my first reason is put the given info into the picture if it's not already there. So this says that angle B is congruent to angle D. All right, I'll put that in the diagram. It also says that C is the midpoint of AE. So C is the midpoint of AE. Well, here's point C, and it's the midpoint of this line. It's not necessarily the midpoint of BD, it doesn't say that, but C is the midpoint of AE, which means in essence that it is going to cut that segment in half. So the given info doesn't specifically say that AC is congruent to CE, but I know that that's true, so I'm going to make that my second statement. AC is congruent to CE, and the reason I can say that is because they told me C is the midpoint, and I know what midpoint means. It means it's going to cut it into congruent parts exactly in half. So what I used here is the definition of midpoint. Okay. All right. Oh, and what I'm trying to do in this proof is to prove the two triangles congruent. I should have said that at the beginning. So looking what I have now, I've got one pair of angles, one pair of sides, and that's a great start, but it's not enough yet. But I can also say that this angle and this angle are congruent because they're vertical angles. Okay, so I can say that angle ACB, that's that top red angle, is congruent to angle DCE, that's the bottom red angle, by the vertical angles theorem. Okay, and now I can finish the proof. I've got two angles and a side, and I'm just thinking, is that side included or not? Well, the two angles I have in this bottom triangle are where I'm putting these green dots. The included side would be the side between those two that joins those two angles, but that's not the side that I have. I have this angle, so it's a non-included side. Same thing in the triangle up top. So it's two angles and a non-included side, and that means these triangles are going to be congruent by the angle side triangle congruency theorem. So the S isn't between the two A's, okay? And then I also want to write what I'm trying to prove exactly the way it is at the top up here. That should be my last statement. So that's going to be triangle ABC is congruent to triangle EDC. Okay. Also, I should say the two steps in the middle, steps B and C, those could be in reverse order. You could have done the vertical angles before the definition of midpoint. But other than that, you'd need this proof as is. You need all four of those steps to complete it. Okay? All right, let's take a look at another. This one's a little trickier because I've got overlapping triangles here. So what I like to do on problems like this, here I'll write in the given, and I could start trying to put the given into this diagram that I have here, but it's going to be a little bit tricky because when it says that AE, that's right here, is congruent to CD, which is right here, it's a little hard to put the congruent ticks on there because if I put a tick somewhere, it wouldn't really be clear if I was talking about the whole segment or just part of the segment. So what I like to do on problems like this with overlapping triangles is first look carefully at the congruent statement and make sure that I'm looking at the correct triangles, because there's a number of different triangles in this diagram. Okay, so I'm going to color this one red. So ABE is this triangle. Okay, and then I'll make the other one green. We'll go the holiday theme here. CBD is that triangle. Okay, so now I know I'm talking about those two triangles. The next thing I like to do is to draw the triangles separately. It makes it a lot easier to keep track of things and to put the given info into the picture. Okay, and then I'll draw this green triangle over here, and that would be C, D, and B at the corners. Okay, so now when I'm putting the given info into the diagram, AE is congruent to CD. Well, that's pretty easy to put into the separated triangles, and it's easier to see what's happening then too. Okay, and I've also got angle CDB. Well, CDB would be right here. That's going to be congruent to angle AEB, which is right here. Okay, the angles aren't so hard to put in the original picture. You could put that in, but it's a little more confusing looking at it. So with the separated ones, I can see, oh, I've already got a pair of sides and a pair of angles just from the given info. So I only need one more piece. Now with overlapping triangles like this, there's always going to be either a shared side or a shared angle. And in this case, this angle at the bottom is in both triangles. It's the bottom angle in both triangles. So I can say then that this angle is congruent to itself. I can say angle B is congruent to angle B, and it's okay to use one letter there because there's only one angle B in the diagram. And when something's congruent to itself, that's the reflexive property of congruence. So I'll just write reflexive there, okay? And then I have enough to say the two triangles are congruent. And I'm going to make my congruent statement just like it is in written above, where it says what we're trying to prove. And that would be two angles and a non-included side. So that means angle, angle, side, triangle congruency theorem. Okay? All right, that's the end of the section, and I'll see you next time.